force of attraction due to sharing of electrons results covalent bonding. It is initially studied by Lewis and Langmuir. Atom shares electrons until it gets 8 valency electrons with other atom or atoms. To get inert gas configuration, it is gaining or losing electrons in ionic bonding. In case of covalent bonding, the sharing is taking place until it gets 8 valency electrons. If you look at electronic configuration of inert gases, they have 8 valency electrons in their valency shell, and we know that mostly inert gas atoms do not participate in chemical bonding, either ionic or covalent bonding. And in modern chemistry, we are preparing compounds of noble gases under special conditions, and that too with a fluorine. Therefore, in those days, the Lewis and then extended by the Langmuir to get back the idea that the electronic configuration with 8 valency electrons or NS2 NP6 configuration is more stable. It's called rule of octet. Noble gas atom has 8 valence electrons except helium. Here atom A, I have written Lewis dot structure of atom A, and how many valence electron it has? 1, 2, 3, 4, 5, 6, 7. Atom A has 7 its own electrons. Atom B has 1, 2, 3, 4, 5, 6, 7. It has 7 valency electrons. Now, the A is giving its electron density or 1 electron, and B is giving its electron, and therefore now I am making this electron pair common for A as well as B. Now, if we start recounting 1, 2, 3, 4, 5, 6, 7. 7 are valency electrons of A, and 8th is an electron obtained due to sharing. Therefore, it has 8 valency electrons and octet is followed. Now coming to B, 1, 2, 3, 4, 5, 6, 7, and it got one more electron, 8, due to sharing, and total number of electrons becomes equal to 8. In this particular case, the molecule AB is formed in which both A and B are following rule of octet. Now take here, make the diagram. Here, commonly shared electron pair. Who is commonly shared electron pair? This is a commonly shared electron pair. Is called bonding electron pair. Commonly shared electron pair is called bonding electron pair. Whatever may be the theory we study in future, the language of covalent bonding will remain same. We use the sharing electron pair as a bonding electron pair. Unshared electron pairs are called non-bonding electron pairs or lone pairs. We also call them lone pairs. Lone pairs of electrons. We also call them unshared electron pairs, are called non-bonding electron pairs or lone pairs of electrons. So lone pairs of electrons or non-bonding electrons are not involved in the bonding. They are not involved in the bonding. Okay. The next point. A covalent bond can be single covalent bond, can be double covalent bond, or can be triple covalent bond. Single covalent bond means one electron pair is shared, which is represented by a single line. Double covalent bond means one electron pair, two electron pair. Two electron pairs are shared. It is represented by two horizontal lines. In triple bond between two atoms, they are sharing of three electron pairs, and it is represented by a triple. So we call in general, it is a single bond. It is called a double bond. We call it a triple bond. So a covalent bond can be single covalent bond or double covalent bond or a triple covalent bond. If it is a single covalent bond, we represent between bonding atoms by one line, and double bond other line, and triple bond by three lines. So a covalent bond can be single, double, or triple bond. Next point. What is electronic domain? Electronic domain is number of an electronic domain can be a lone pair, can be a single covalent bond, or electronic domain can be a double covalent bond, or it could be a triple covalent bond, or it could be a single electron. It could be a single electron. So electronic domain can be a lone pair, single covalent bond, double covalent bond, or a triple covalent bond, or single electron. It is defined around an atom. It is defined around an atom in the molecule. So what is electronic domain? Electronic domain can be a lone pair, can be a single covalent bond, double covalent bond, or triple covalent bond, or it could be a single electron. It is defined around an atom in the molecule. Let us see an example above. Here, let us see the example here. Total number of electronic domains around A: one electron pair, two electron pair, three electron pair. These are non-bonding electron pairs. This is called bonding electron pair. So A is surrounded by four electronic domains. Here B is surrounded by three lone pairs, three electronic domains, plus one bond pair. Again, 4 electronic domains. Suppose in one situation, let's consider one molecule Xe, double bond O, F, and one lone pair, and here one lone pair. Now, around xenon, you can make all these structures on your own in today's class itself. Don't bother. Around xenon, can you count how many are there? One lone pair. This is a second lone pair. This is single covalent bond. This is single covalent bond. So it's a 4. This is a double covalent bond, 5. So around xenon, there are 5 electronic domains. So around xenon, there are 5 electronic domains. Out of the 5 electronic domains, 2 are lone pairs, 2 are single covalent bonds, and 1 is the double bond. This is how we use the language of covalent bonding. Origin of force of attraction, a simple model to understand a covalent bond. Actually, how this covalent bonding force arises. Consider energy changes when one hydrogen molecule is formed from two isolated hydrogen atoms. Copy that. Consider energy changes when one hydrogen molecule is formed from two isolated hydrogen atoms. Please note that hydrogen atom do not follow rule of octet because the hydrogen atom has 1 electron, another hydrogen atom has 1 electron. Now they commonly share their electron pair, so we get hydrogen molecule. Now we are going to replace hydrogen, a single bond, to tell that 1 electron pair has been shared between 2 hydrogen atom and HH. Consider energy changes when one hydrogen molecule is formed from 2 isolated hydrogen atom. So where do we get this force that holds the 2 hydrogen atom due to sharing of electron pair? Here, important thing to be understood that this bond should have 1 electron spin up and electron spin down to follow Pauli's principle. Not only atoms, Aufbau rules, Hund's rule, and Pauli's principle are followed by molecular bonding electrons also. Not only at atomic electrons, the atoms of molecule also follow Aufbau, Hund's rule, and Pauli's principle. Therefore, a bonding electron pair must have both electrons with opposite spin, and therefore they follow Pauli's principle. Now, what happens? Let us see. When hydrogen atoms are coming closer and closer, we know that hydrogen atom has a 1 proton at nucleus, and other hydrogen atom also has 1 proton in its nucleus. And I am not talking about neutron because neutron is neutral. It doesn't attract or repel. Now, time being, let us consider only 1 orbit. And here also I am considering 1 ground state orbit. Of course, now we know that this circle in fact represents 1s orbital. This is 1s orbital, and this is 1s orbital, in which the electron has a chances of existing with the probability of 90 to 95%. Let us suppose our electron on average consider in this zone, and here the electron is in this zone. For time being, I am labeling these hydrogen atoms, one as H1 and other hydrogen atom as H2. For time being, to distinguish, I am calling the first hydrogen atom H1 and other hydrogen atom H2, and I am calling 1s1. It is H1 atomic orbital, and here 1s1, 1s orbital of, 1s2. Is 1s2. 1s2, that is hydrogen atomic orbital, second hydrogen atomic orbital. When both atoms are coming closer, when these are coming closer, as they are approaching closer and closer, initially attractive forces starts. Attractive forces, where they operates from. Example, now the proton and proton, they get repelled. There is a repulsion. And between electron and electron, there is a repulsion. When electrons are coming closer, when hydrogen atoms are coming closer, there is a repulsion starts operating between two nuclei, and also the repulsion starts operating between the two electrons. But the nucleus of H1 start attracting the electron of H2 atom, and simultaneously the nucleus of second hydrogen atom starts attracting the electron of first hydrogen atom. So let us call this electron E1, and let us call this electron E2, and let us call this nucleus is N1. Let us call the nucleus is N2. Therefore, when two hydrogen atoms are coming closer, we are developing E1, E2. What are the condition? What are the type of what are the kind of forces? Repulsions between N1 and N2. Again, we are experiencing repulsions, where in case of N1, nucleus 1, with electron of the second hydrogen atom experiencing attraction, and the nucleus of second hydrogen atom, we are calling N2, attracting the electron E1. This is also called attraction. Initially, the hydrogen atoms have to come closer. This is only possible initially there are attractions. And unless there are initially net attractive forces, the two hydrogen atoms will not come closer together. Now, initially, attractive forces starts operating, but here is a condition. Initially, attractive force starts operating if and only if E1 and E2 have parallel spins, anti-parallel spins, opposite spins. Anti-parallel spins. So you got the idea? So when two hydrogen atoms are coming closer, there is there are attractive forces. They only start unless the electrons are having anti-parallel spins. If they are having parallel spins, initially there are repulsive forces. Therefore, there is no formation of covalent bond between two hydrogen atoms. That is what I said earlier in Pauli's principle, that the electron pair, in a bonding electron pair, the electrons must have opposite spins or anti-parallel spins. Initially, the attractive forces starts operating between hydrogen atoms if and only if E1 and E2 have anti-parallel spins. If E1 has up and E2 should have down, then how could be energy change? Now let us make energy diagram. Let us make energy diagram. So variation of energy. With internuclear distance. Variation of energy with internuclear distance. Let us make this is y-axis. This is x-axis. Let us say D. D is interatomic distance or internuclear distance. This is energy. In strictly speaking, we generally call it potential energy. We should call it potential energy. Let us have a line. This line corresponds to 0 point energy. We represent generally it by E0. Most of the cases, we set E0 value as 0. Generally, we say that E0 value is 0. When hydrogen atoms are infinitely large, let us say this is infinitely large. So here we have two hydrogen atoms, H, and another hydrogen atom, H. Now, let us have some distance. So, and let us call this is D infinity. Here D infinity means hydrogen atoms are infinitely separated. When two hydrogen atoms start coming closer and closer, then what happens? The energy of hydrogen atoms gradually decreases and reach certain minimum value. And if you are pushing two hydrogen atoms very closer and closer, till now we have attractive forces. But if you still move the hydrogen atoms very closer and closer, then what happens? The repulsive forces start dominating. When repulsions start operating, then energy will go on increasing. Therefore, initially there are attractive forces. The energy gradually decreases, reaches minimum, and if you push the hydrogen atoms, the energy gradually increases. The decrease in energy, we actually denote this D as D equilibrium, which is here. D equilibrium is called bond length. We call it bond length, which is distance between two bonding atoms. So distance between two bonding atoms. Therefore, The D equilibrium is a stable state where hydrogen molecule exists. So at this point, two hydrogen atoms form a covalent bond. If we move in this direction, suppose if we move in this direction, then energy of hydrogen molecule increases. Or if you decrease the distance between two hydrogen atoms, then also energy increases. Now here, I think you know the basic definition. Force is equal to minus dV by dr. Force is equal to minus dV by dr. dV by dr is here energy can be called, or we may call it V naught. You may also call it V naught, potential energy or energy V naught. F is a minus dV by dr. dV by dr is a slope. Let us suppose I compute the slope at such a particular point. So let us say this is the slope drawn corresponding to the point D1. What is the slope? Positive. So at D1, dV by dr is positive. If dV by dr is positive, from the definition of force, minus dV by dr, force becomes negative. Negative force means it's a attraction. Conventionally, if force is negative in electrostatic, you may come to know that the force takes negative, we call it attractive. Therefore, for the bond lengths between D equilibrium to D infinity, there is a continuous attractive force. Now let us make the slope at some other point at a distance less than D infinity. That's a slope. Now what happens? Let us say the corresponding D is D2. Now at D2, can you tell me the slope? dV by dr, negative. If dV by dr is negative, negative into negative, positive. Force becomes positive and it indicates repulsion. It indicates the repulsion. And now let us take exactly this particular point S at D equilibrium. dV by dr, slope is 0. Therefore, net force is 0. So neither attraction nor repulsion, the net force is 0. At the same time, if you compute the energy released and this particular yellow line is the net energy released. See, this is initial energy, E0. This is the energy. Finally, the two hydrogen atoms are having together. Initial energy of two hydrogen atom is E0. The final energy of hydrogen atom is this value. Therefore, when hydrogen molecule is formed, equivalent of this energy would have been released. That is what we are calling bond energy. Therefore, bond energy generally used for gaseous state. The bond energy and bond energy terms we generally use only in gaseous state. Bond energy is energy released when 1 mole of bonds are formed. So bond energy is amount of energy released when 1 mole of bonds are formed. Let us say this energy is let us mark this energy is E H2, that is energy of hydrogen molecule. Then bond energy becomes equal to, here bond energy is E naught minus EH2 molecule. This energy called E naught minus EH2. This is approximately, I'm just rounding off, this is around 430 kilojoules per mole. In case of hydrogen, it is 432 kilojoule per mole. Once again, let us see what happened. We are going to study from origin of force of attraction, origin of force of attraction. We are taking a simple model to understand a covalent bond. Therefore, I am considering the simple molecule. Consider energy changes when one hydrogen molecule is formed from two isolated hydrogen atoms. They are infinitely separated. Then both hydrogen atoms commonly share an electron pair that results in the formation of hydrogen-hydrogen single bond. Please make a rule that in any covalent bond, the bonding electron pair must have opposite spins to follow Pauli's principle. When two hydrogen atoms, let us say H1 and H2, are coming closer together, there exists repulsion between N1 and N2, the nuclei of H1 and H2, and E1 and E2, the electron of E1 and E2, the electrons of H1 and H2 respectively. Simultaneously, the first nucleus attracts the electron of second hydrogen atom. The nucleus of second hydrogen atom attracts the electron of first hydrogen atom. Consequently, initially attractive force starts operating if and only if E1 and E2, E1 and E2 have anti-parallel spins. This is mandatory conditions, anti-parallel spins. Now we are plotting variation of energy with intermolecular distance. Let us consider this is y-axis, energy is plotted, and let us consider this is x-axis where interparticle distance is taken. These are two isolated hydrogen atoms. Our hydrogen atoms are initially having energy we call E naught or V naught. Generally, we refer this E naught value is 0. If generally they don't mention anything, then for most of the cases, we take E naught as a 0. When two hydrogen atoms are coming closer, initially the attractive forces starts dominating and energy becomes minimum, and then energy starts increasing. Therefore, here we are using D infinity to indicate that hydrogen atoms are infinitely separated. Therefore, they have a corresponding energy E naught. Now, by definition, force is equal to minus dV by dr. Now, dV by dr is a plot drawn between potential energy versus distance. Here R is equal to D. Here we may use D, or here we use dr. I mean, it's a, you can use R. Okay, it could be R, something R. You may call it R. Okay, that's nothing wrong. It is our convention. We can use anything. Now let us make a slope at D1. Then the slope is clearly positive. If dV by dr is positive, the negative of positive is negative. Therefore, in this zone, there is attractive forces. Where exactly at point D2, the net force is 0 because slope is 0. At point D2 or at any point less than D equilibrium, it is having negative slope. dV by dr is negative. Negative minus negative, it's a positive. Therefore, here there exist repulsions, and this is zone, there exist attractive forces. Therefore, when hydrogen molecule is formed, initially having E naught, generally what we take E0 to a final state where we call energy of hydrogen molecule. This difference is also called bond energy. This difference is also called bond energy. You please copy the notes after this class. I post the notes, okay? Because today we have a little time, so we cover up the required syllabus. Okay, anyway, I post the notes, then you can copy it clearly. So you got, that is the reason why energy of hydrogen molecule decreases. And this bond energy that is releasing. In fact, energy releases when there is attraction. The logic is simple. You always use this rule by bind flow, by blind method. Every time when there are attractions, when compared to previous state, the energy must decrease. Whenever there are repulsions compared to the earlier state, then there must be increase in energy. When two hydrogen atoms are coming closer, and here I am further making very clear, these hydrogen atoms are coming with anti-parallel spins. Therefore, energy decreases until they come closer to reach their bond length. The energy released when one mole of bond is formed is called bond energy. In case of hydrogen, this double-headed, this bond energy is approximately 432 kilojoule per mole. Now, what happens if hydrogen atoms are coming with anti-parallel spins? Let us again make a diagram. And this is 0 point energy. We generally call it E naught. And here we are making interparticle distance D. And hydrogen atoms are first hydrogen atom and second hydrogen atom. Now the variation of energy can be represented. This is energy where both hydrogen atoms are coming with a spin up parallel, anti-parallel spins. Suppose if they are coming with anti-spins, then their energy increases, and therefore this is the energy if both hydrogen atoms are coming with a parallel spins. Because with a parallel spins, initially the repulsive forces dominates, and nowhere the attractive force starts operating. Nowhere attractive force start operating. Therefore, be clear about it. If the bonding electron pair has a parallel spins, there is no question of attractive forces operating. Okay? Now, this is how we simply understand the force of a covalent bond and how the bonding electron pair can hold the two atoms. Now here we need to go into very deeper course of the covalent bonding and how these attractive forces start operating and how the repulsive forces start operating. If you look at our model, we have considered a simple electrostatic model by assuming that the electron is somewhere revolving around the nucleus, somewhere else revolving around the nucleus. Here we assumed that the electron is revolving and a simple electrostatic model. But in reality, the electrons are not simple particles. We know that they have a dual nature. They have both particle as well as a wave nature. And for microscopic particles, simple Coulomb's theory or Coulomb's attractive forces cannot be applied. And therefore, to obtain the exact energy data, how energy changes with the bond length, we need to use some theories. They can be valency bond theory. It can be valency shell electron pair repulsion theory. It can be molecular orbital theory. And these theories will make quantification. Quantification means exactly to tell how much energy drop and why it is dropped. And what is the reason for initial attraction. Why initially there is repulsion with the parallel spins. Why there is attraction initially with anti-parallel spins. How these magnitudes are compared. This can be quantitatively done by using some theories, and these are very specific theories that we discuss maybe a day after class. So here we are not quantifying, we are qualitatively understanding the force of covalent bond rather than the quantitative understanding. You got? So in this description of the 20 minutes, what I have done, I made a qualitative description of the nature of covalent bond and the covalent bond forces, but I didn't make any quantitative description. The quantitative description can only be done by knowing the perfect theories of covalent bonding. By knowing perfect theories of covalent bonding. Now, before going into the theories of covalent bonding, we need some extra material and extra knowledge that here I am going to start. The heading is excited electronic configurations. Atomic configuration. To understand the theories, please note that here why anti-parallel the attractions are starting up and why with the parallel the repulsions are starting up, that we only understand by theories. So right now I didn't teach you how this principle is acting to form a covalent bond. So these theories only can be understood by using theories. Subheading excited electronic atomic configurations. Here take an important note, not correlated to microstates. Microstate means exact energy of electron. So we are not going to use the exact energy of electron. Here we are just finding electronic configuration and distribution. So not correlated microstates. I am taking excitation in terms of electronic configuration. Now let us take alkali metal. We don't want to consider alkali metal. Let us consider two groups, second group metal. Here I am going to write always valency electronic configuration. I don't want to know the core electronic configuration. Valency electronic configuration can be written NS2 NP. NS2 and NP for second group electron, NS2 to NP. Now what happens? This is a ground state electronic configuration. This is called ground state electronic configuration. Now supply energy, give some energy. Then what happens? One of the NS electron will be excited to NP up and with a spin up. This electronic configuration is called excited electronic configuration. In strict, we call it first excited electronic configuration. First excited electronic configuration. So in second group elements, in ground state, they have only 2 electrons. They do not form any covalent bond because to form normal covalent bond, they require unpaired electron. Therefore, alkaline earth metals, second group at elements, undergo excitation, first excited state, 2 unpaired electrons, therefore they can form 2 covalent bonds. Here covalent bonds means a normal covalent bond. So we don't specify abnormal things. Here we always specify normal things. Therefore, as there are 2 unpaired electrons, second group elements form 2 covalent bonds in first excited state. Now let us consider third group. Here 13th group. We are not dealing with the bonding of the D block elements. So let us go to 13th group, which is also called 3A group. In case of 3A group, again, this is energy, their outer electronic configuration, NS, NP. Now let us place 2 electrons in NS and 1 electron in NP. This is called again ground state electronic configuration. It has 1 unpaired electron. It has 1 unpaired electron. Therefore, in this electronic configuration, 13th group element can form 1 covalent bond. It can form only 1 covalent bond. Now, supply energy. Now supply energy. Then what happens? NS. This is the NP. One of the electron get excites to NP state. So now this electronic configuration is called first excited state. Here how many unpaired electrons we have? 3 unpaired electrons. Therefore, it can form 3 covalent bonds. So in ground state, 13th group element form 1 covalent bond. In first excited state, it can form 3 covalent bonds. This becomes complex as we are increasing the group number. Let us take 14th group element. 14th group is nothing but 4th A group element, carbon family. If you make energy diagram, NS2, so it is going to be NS2, NS, NP, NP. It has 2 unpaired electrons. Now supply energy. Then it gets excited. This is NS. This is going to be NP. One of the NS electron will be excited to NP. So this is called ground state electronic configuration. First excited state, electronic configuration. Here 2 bonds, 2 covalent bonds. Here in this first excited state, atom can form 4 covalent bonds. Generally, 14th group elements would like to form 4 covalent bonds. Generally, 14th group elements would like to form 4 covalent bonds. That is the reason in Lewis dot structure, you see, we have used 4 isolated dots. We don't pair the dots in Lewis dot structure of 14th group element. Similarly, in 13th group elements also, we have not paired the 3 dots. We kept the 3 dots isolated. Why do we kept? Because the 13th group elements generally form 3 covalent bonds. 14th group elements generally form maximum 4 covalent bonds. Now let us see a complicated system. We are entering into 15th group. That is nitrogen, phosphorus, arsenic, antimony, and bismuth. Their general configuration, NS2, NP, So it has NS2, NP3. Now we make another NS NP, NSNP, ND, only possible for third period after. Because in second period, 2s, 2p, we don't have a 2d. But for a third period, 3s, 3p, we have a 3d. Now, let us excite one of the NS electron will be excited to ND. One of the NS electron will be excited to ND. So, in ground state, this is we call ground state electronic configuration. First excited electronic configuration. Here it forms 3 covalent bonds. Here it forms maximum 5 covalent bonds. So 15th group elements form 3 covalent bonds or 5 covalent bonds. 3 unpaired electrons, 3 covalent bonds in excited state, 5 unpaired electrons, 5 covalent bonds. Please note that this is only possible only for third period element because there are 3d orbitals. Now moving to 16th group, oxygen, sulfur, selenium, tellurium, NS2, NP4. Now NS2, NP, ND, NS, NP, ND. Now what happens? Let us make the 2 electrons the same. And one of the NP electron is excited to ND orbital. Now what may happen? NS, NP, ND. This time like you can excite one of NS into ND. 1, 2, 3, 4, 5, and 6. So this is ground state electronic configuration. First excited electronic configuration. Second excited electronic configuration. Here it forms 2 bonds. Here it forms 4 bonds. As here 6 unpaired electrons. Here it forms 6 bonds. Now let us take 17th group. 17th group, halogens, fluorine, chlorine, bromine, and iodine. We have NS, NP, and ND. Energy increases. So NS, NP, 3, ND. Its electronic configuration, NS2, NP5. Now, let us make many excitations we can make. These all are NS orbitals. NP, 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 ND, and again 2, 3, 4, 5 orbitals. Now let us excite first. So there is one more electron here, right? NS2, NP5. NS2, NP4, one electron is excited. NS2, NP3, ND2. 2 electrons are excited. Now NS electron is exciting. Therefore, we got 3 electrons. This is ground state, first excited state, second excited state, third excited state. In ground state, 1 bond, first excited state, there are 3 unpaired electrons. They can form 3 bonds. In second excited state, they can form 5 bonds. In sixth excited state, they form 7 bonds. Here, what is the note? Fluorine can form only 1 bond, and here also oxygen can form only 2 normal covalent bonds. It can form only 2 normal covalent bonds. Some extra other type of coordinate covalent bonds are also there. That type we specially study. But right now, everything I am teaching about a normal covalent bonds. We are not going to abnormal covalent bonds. Now, finally, we are coming to 18th group. So, 18th group. In case of 18th group, again, NS. Here we get a many NS. We can make many excitations. NP. So all these are NP. And we have ND. And here also ND. And here also ND, 5 orbitals. So this is NS, NP, and ND. Now go on filling. NS2, NP6. Now let us excite one of the electron from NP into ND. Now one more electron into ND, and next one more p electron. Therefore, we have 3, and now we are exciting to get 4 electrons. This is ground state electronic configuration, first excited electronic configuration, second excited electronic configuration, third excited electronic configuration, fourth excited electronic configuration. Here, 0 bonds in ground state. Inert gas cannot form any bond. Here, 2 bonds. Here, they can form 4 bonds. Here, they can form 6 bonds, and here they can form 8 bonds. Now let us make a note. There is oxide ion, O minus 2 ion. Sorry, O minus ion. Let us say there is a O minus ion. How many bonds are formed by O minus ion? What we do? We make it configuration. For oxide, it is 2s. Sorry, 2s. 2. For oxygen atom, it is 2p4. Because of having 1 unit of negative charge, we need to add 1 electron. Therefore, it can form one covalent bond. It can form one covalent bond. So no excitation. Why no excitation? No 2d orbitals are possible. Therefore, O minus ion can form only one single bond. O minus ion can form only one single bond. This is all for today's class. What do you do? These notes once you go through and you make very clear about the ground state and excited electronic configuration and how many bonds formed by each element. Please make sure that in any group, from 13th group after, in any group, 14th group after, you see that, for example, 15th group, any 15th group element minimum can form 3 bonds, and 16th group elements can form 2 or 4 or 6. 17th group element can form 1 or 3 or 5 or 7. 18th group element can form no bonds, 2, 4, 6 or 8. These are number of covalent bonds formed by an element. Okay? Now, last this topic. Another note. Excited electronic configuration of oxygen atom. We use this particular cases. We have 2s2, 2p4. Now let us apply energy. You add energy, then oxygen atom will reach an interesting energy state. 2s, 2p. This electron gets paired up. 1, 2, 3, 4. So it created an empty orbital. An empty orbital. Please, very important about this empty orbital. So here 2 electrons in ground state. 2s2, 2p, all electrons are paired up. Therefore, here it is creating an empty orbital. Okay.